trapezoidal rule. So we've already seen how integration tells us the area under a curve, but there are other ways to approximate the area under the curve, and the trapezoidal rule is one way to do that. So let's have a look. If we had a function, say like this, and we wanted to find the area between here and here, we could connect these 2 points and find the area of that trapezium, and that would be an approximation to the area under the curve. We would have this little extra area, but it would be an approximation under the curve. Now, instead, if we were to split these points in half and then connect this point and this point and this point and this point, we'd have 2 trapezium there. And we could find the area of these 2 trapezium, and it would give us a better approximation than just using 1. We could even go another step further and use 4 trapezium, connect here and here, here and here, here and here, here and here, find the area of all 4 of them, add them together, and that would give us a better approximation. That's exactly what we're doing here. We're going to be splitting up an area that we want to find into trapeziums and finding the areas of all of those. But we have a formula to help us do this. So you might see a couple of different formula, and they're all going to be a way to approximate the integral from a to b of f of x dx, where a and b were the bounds of your area. So one way to approximate the area is using the formula b minus a over 2 outside of the f of a plus the f of b. Another way is using h over 2 outside of y0 plus 2 times all your middle y values plus yn, which is your last y value. Now, what do some of these things mean? Well, b and a just represent a and b here. And now f of a and f of b are actually the y values at a and b. So it would be this value here for y and this value here for b. And that's the same as all these y values here as well. So they're the y values at your points where you're splitting up the function. And we've also got a h here, and h, depending on how many times you split it up, h will be the height of all your trapezium. And one way to get the height is just to do b minus a over n, where n is the amount of trapeziums you're using. So this is the number of trapeziums. So in this case, if we were splitting it up into the 4, your n would be 4. And it's important to note, if you were splitting it up into 4 trapeziums, you'd have 5 y values, 1, 2, 3, 4, 5 for 4 trapezium. So let's look at an example. Let's look at approximating 0 to 2 of the square root of 4 minus x squared dx. Well, let's graph it out to see what we're actually dealing with. Well, hopefully you can recognize that the square root of 4 minus x squared is the top half of a semicircle of radius 2. So this would be 2, 2, and minus 2. And if we were going from x equals 0 to x equals 2, well, x equals 0 is here and 2 is here. So the area we're concerned with is this one here. Obviously, we could it's just a quarter of a circle, and we could do that normally, but we're going to learn how to do it using the trapezoidal rule. And first we're going to do it by using two subintervals, which is just another way of saying splitting it up into two trapeziums. So it's going to look something like this, where we're splitting it in the middle and making two trapeziums like that. So I like using the formula to approximate as h over 2, y is 0 plus 2 times your middle y values plus your last y value. And it helps to make a table to look at all these. So this is exactly what we're going to do. And because we're doing two trapeziums, that means we need 3 y values. So we're going to do 4 columns. One for x and one for y. So we're going between 0 and 2. So we need to work out the height of each trapezium, and remember the height is b minus a divided by the number of trapezium. So the height's going to be, well, it's 2 minus 0 divided by, we want 2 trapezium. So 2 minus 0 is 2, over 2 is 1. So the height of each one is 1, which means you just keep adding the height every time you go across. Here we only have to do it once. So 0 plus 1 is 1, and 1 plus 1 is 2. So we've done that correctly. And now you just need to sub in x into your function to get the y value. So we're going to sub 0 in first. So 4 minus 0 squared is 4, and the square root of 4 is 2. Now we can sub 1 in. 1 squared is 1. 4 minus 1 is 2, so we get root 2. And we can leave it as root 2. Now we can sub 2 in. 2 squared is 4. 4 minus 4 is 0, and the square root of 0 is 0. And there's our y values. So our first one is y0, then y1, and then y2. So we can approximate our area. We can plug everything in the formula. So our height we know is 1 over 2. Outside of y0, well, we know y0 is 2. Plus 2 times all our middle values. Well, there's only one value in the middle, and that's root 2. So it shouldn't be root 2. That made a mistake, because we get 4 minus 1 squared, well, 1 squared is 1. 4 minus 1 is 3, so we actually get root 3 there. So that should be root 3. Plus, this is just our last y value, and we only have 3, so it's just this y2 here, which is 0. And now we can go ahead and evaluate this. So we get a half times, well, 2 plus 2 root 3. And we can expand this out. So half times 2 is 1, and a half times 2 root 3 just gives us root 3. So we get 1 plus root 3, which approximately equals 2.732 as our approximation to this quarter of a circle. So this time we're going to try the same thing, but using 4 subintervals. So it's same function, same limits, but we're going to use 4 subintervals. So remember, our height is b minus a over n. We're going to approximate the area with the height over 2 outside of our first y value plus 2 times all our middle y values plus our last y value. and we're going to do a table to help us out. So since we have 4 subintervals, that means we need 5 y values. So let's do a table with 6 columns. So we get our x and our y values, and we're between 0 and 2. So now we just need to work out the height. So we know our height is going to be b minus a over n, our subintervals, which is 4. So 2 minus 0 is 2, and 2 over 4 is a half. And that's what we need to keep adding across as we go. We need to keep adding a half. So 0 plus a half gives us a half. Add another half, get 1. Add another half, get 1.5. And add another half and get 2. So we've done that correctly. Now we can go ahead and sub these x values into our original function to get our y values. So if we sub 0 in, we get 2. If we sub a half in, we get root 3.75. If we sub 1 in, we get root 3. Subbing 1.5 gives us root 1.75, and subbing in 2 gives us 0. And this is going to be y0, y1, y2, y3, and y4. And we're ready to sub everything we know into the formula. So our area is approximately going to equal, well, the height is a half, so we get a half over 2 outside of our first y value, which is 2. It's this one here. Plus 2 times all our middle y values. Well, our middle y values are all these y values in the middle, so not the first one, not the last one, all of them in the middle. So we get plus 2 times, and what we have to do with the middle y values is add them all together. So we get root 3.75 plus root 3 plus root 1.75. And then finally, we're just going to add our last y value in. And that can all go in the calculator, and you'll get approximately 2.996 as your approximation to the area for that quarter circle, which is a little bit bigger than the last one. The last one was 2.732, and this should be closer to the real value. And remember, it was just a quarter of a circle, so let's just investigate. So it was a quarter of a circle with a radius of 2. So the area actually equals a quarter pi r squared, where the radius was 2. So that's just a quarter times pi times 2 squared. And 2 squared is 4. We'll cancel out with that 4. And the actual area is equal to pi, which we know is approximately equal to 3.14. So you can see it is getting closer and closer to that actual value.